Okay, this little video is about the word tensors, or the concept of tensors, which I would say is just a fancy word linear functions. Okay, at least in dynamics and sort of classical mathematics, it's just a word that essentially means linear functions. For instance, you could have something called an order 1 tensor, which would have vectors as input and output scalars, in other words, real numbers. Order 2 tensors, which is sort of what we would focus on right now in more detail. Order 2 tensors are functions, linear functions that take vectors to vectors. Okay, the input is a vector, the output is a vector. Now, what do we mean by a linear function? So let's recall what the definition of a linear function is. A linear function satisfies the following sort of two conditions. Let's say the linear function of vectors, let's say, satisfies the following two conditions. Okay, this is what we mean by a linear function. So if you have a linear function L as a function of some vector V, then, so this is a function of vector V, this satisfies the following conditions. Condition number 1 is that if you have two vectors, A and B, then that's equal to the function. So the function operated on the sum of those two vectors is equal to the sum of the function operated on the individual vectors. So L of A plus B equals L of A plus L of B. This would be called superposition. Okay. And then the second condition, which you can sort of also think of as a version of superposition, but has to do with scaling, linear scaling, is if you have a scalar times a vector, so where C is a scalar, and then operate that quantity by the function L, then you have that's equal to C times L of A. Okay. Okay, so these are the two main properties of linear functions. Now let's briefly look at what order 1 tensors are and order 2 tensors are. Both of these are actually quite familiar to you, but it's good to sort of understand this sort of more abstract mathematical idea of tensors as general background for some of the things that we're going to talk about. Okay. So let's briefly talk about order 1 tensors. Okay, and we will show that they're very similar to basically dot products with a vector. Okay, so this is not obvious, like what does this mean? We'll expand on what that means in a minute. Okay, so imagine a linear function from linear function L from vector v, vectors to scalars, right? So where w equals some function L of v now this is a vector, this is the linear function or the tensor, and then of course this is a scalar. Okay, so imagine a function like this. You can ask the question, what is the most general linear function that has this property? Okay, so let's consider some vector v equals, and let's say it's represented in some coordinate frame. Okay, and then we see how that vector gets transformed by this linear operation. Because it's a linear function, we must have, well, let's just substitute this in. Vx and Vy and Vz are of course scalars, right? So and Ex, Ey, Ez are vectors. So let's because Vx, well, first of all, we can expand this out because of linearity into these three quantities. And then, so essentially using relationship 1, and then each of these can be broken up into Vx times L of Vx, Vy times L of Ey, etc. using this relationship. Okay, so this is going to be equal to Vx L of Vx plus Vy L of Vy plus Vz L of Vz. Okay, so that's essentially L of any vector v. Now denote L1 scalar equals L of Ex. L2 is L of Ey. L3 equals L of Ez. Okay. In other words, you define three scalars that are obtained by operating the function L on the three coordinate axes, Ex, Ey, Ez. Then this relationship becomes, so let's call this equation 3. 3 becomes the function L becomes Vx. Actually, let's call this, I shouldn't have called it L1, L2, L3. Maybe I should have called it Lx, Ly, Lz. So Vx, Lx plus Vy, Ly plus Vz, Lz. Okay, so that's what that becomes. This equation becomes that, becomes this thing. Now, of course, what does this look like? What does this quantity look like? Think about it for a second. This quantity looks like the dot product of a vector v and a vector L. And this expression would be the expression that you get if both v and L were represented in the same frame, right? So this is, of course, equal to Vx Ex. Let me rearrange it. So this expression could be written in the following form: lxex plus lyey plus lzez dotted with vxex plus vyey plus vzez, okay, or some vector L dotted with V, okay. So the most general order 1 tensor, the general order 1 tensor, by which we mean something that takes linear function that takes a vector to a scalar is a dot product. Okay, so that's an important lesson. Now let's look at order 2 tensors, which have vector inputs and vector outputs. Okay, we shall do that in the next little video.